Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los. Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los.
Das ist das, was ich über das Spiel gerade kriege. Achso, jetzt kriege ich ein Bild.
Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los. Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los. Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los. Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los.
Kann ich das ein bisschen weiter nach vorne oder habt ihr das? Kann ich das ein bisschen weiter nach vorne?
Song und los! Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los! Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los! Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben.
YouTube gehen, den Channel gucken und mir sagen, ob man uns hört. If you have a question, ask somebody else. Do you sit somewhere? I'm not sure. Einfach aus. Hi, hi, hallo. Uno, dos, tres, cuatro. Hörst du das?
Ja.
Dankeschön, wir sind die Cantina-Band. Wenn ihr Songwünsche habt, ruft sie einfach. Spielt denselben Song nochmal. Alles klar, denselben Song und los.
Okay. Hi everyone. Welcome back. I'm Pierre from Cybus. And yeah, welcome to the final presentations. We'll have short presentations from each team. We'll have a small break where the jury will come together to choose the award winners. We'll have the award ceremony, and after that we'll have a few drinks and of course a group photo. So first, let me thank you all for being here. We're very, very happy. I'm very excited to be here and to experience the final presentations with you. I just got the last numbers from the usage of the Cybus and the number of messages used, etc. Overall, in this weekend, we have over 16 million messages who have been consumed. From the teams, around between 5 and 6 million, so 5.6 million used messages by all teams. We've got a few outliers here. Pfannenberg actually used 3 million of those. Somehow they subscribe to lots of data. Actually got a hold of Burkhard there to get all the permissions. Yeah, so we're very excited about this. Each team will have 4 minutes to present their idea, their solution, and after 5 minutes we'll have to take a cut. So please keep to the 4 minutes roundabout. So first to present, I'd like to welcome Stefanie and Stefan from Tinkerbells. They've been working with Tinkerbots and quite some sick data. Hey, little round of applause.
Yeah, hello, Stefanie, Stefan. We are the Tinkerbells, and we decided to play with the Tinkerbots and see what we can do. We made many mistakes. We had fun, and it was real winning in the end. So much winning. Thing is, initially the idea was, what can we do with the Tinkerbot? We have several sensors here. Especially, we thought about using the RFID sensors. Maybe use the 2D scanning RFID sensors to locate objects or RFID tags in a room. We figured that they are using, if I'm not mistaken, just a two-dimensional plane. So you can't really have a three-dimensional location of an object. So that didn't work for us. And then we decided to use the laser scanners to identify if an object entered the area and stays there. And then we wanted to identify that there is an object with a certain width in a certain distance. And then the little bot should move to it and try to poke it. And yeah, and that was what we've been working for. So we will go a little bit introduction to the techniques we use, and then yeah, we are hopefully done in the time we have. Okay, maybe Stefanie will talk about what we did with Node.js.
initialized it, and then I just took care of the Tinkerbots. There's a base Tinkerbot, then we implemented a class for the stalking, well, moving Tinkerbot, and we had different modules, actors and sensors, and they had also base classes, and we had a base connection which had the connection to the MQTT connection to Energie-Campus Cybus IO, and everyone used that one connection. Yeah, and you can, with the Tinkerbot, you can assign to it the different modules you attached here, and or just initialize the modules, and you have to pass in the Tinkerbot it belongs to. So they know each other. The Tinkerbot knows its modules, and the modules know their Tinkerbot, and so they communicate easier. Yeah, and then we just implemented stuff that we needed. Yeah.
Yeah, so the thing is, Stephanie is too modest. I'd really like to call that what she developed, a frameworkish approach to use the MQTT library, which was developed by Burkhard, I think, to map the Bluetooth protocol, which is usually used to use the Tinkerbot with the MQTT broker here, so you can basically use all the Node.js classes to define your Tinkerbot and work with it. That's what we did. We have the components, as Stephanie said, and then we used the LMS sensor in the upper floor, which I figured out in the end has 1,401 data points mapped to the 190-degree coverage of the sensor. So we mapped this to 6 data points per degree. We evaluated the data we got. These are packets with XY coordinates. We discarded them. We just looked at the time and need to speed up. So with this, we find out in which direction and which distance an object is. Then we try to calculate if it has the correct width with the good old Pythagoras. And then we use a formula to find the angle we have to steer to hit the point in the distance. This is a screenshot of the video, which I could show that the bot is driving actually to its destination within a sane safety distance.
20 seconds.
We are over?
You've got 20 seconds to show.
Oh, okay. So then let me speed this up. There he comes. Yeah.
It's a racer.
Yeah, it's a racer. And there he goes. Ooh, and then he drives, but he keeps his distance. We added an offset, because usually you will have here some grabber or something like that, with, which extends its whole length, so he stops here. Yeah. And that would be the short video. It's hard to show the living code, and so, yeah.
Thank you very much.
Yep, thank you.
So next up is Team Orange Mix. So Sergey, Wolfgang, and Johan. They took a 3D printer from TE and combined it with IBM Bluemix to show some magic.
Oh. Okay. Ich habe einen
Okay. Ja, also das filmen wir.
Okay.
Also hier gucken.
I have to look here. For me, it's, so we're Team Orange Mix, and we're pretty international, so I'm talking in English, so that my teammates can also understand it. It's Sergey, Johan, and myself, as already said. task we were working on was to visualize and analyze time series data of a 3D printer. So this is the 3D printer, something like 2 meter high and pretty big, and printing things like that. And motivation was we want to better understand the data coming out of the printer, and in the long term it's for optimization of the production, predictive maintenance and all that kind of stuff. But we wanted to do kind of the first step, getting an idea of the data. The setup is, so we have the printer, it has an OPC-UA interface. We used some software to collect all the data, store it in a Mongo database, and then at some point in time, after 6 weeks of tracking the data of 200 data points, we exported the data into a 11 gigabyte CSV file, and then that's what we did in preparation, and then Cybus also did something in preparation. They put this into their database, and were very nice and implemented a small replayer, which we could just with MQTT start and say, okay, we want to simulate this chunk of data starting here and going to a certain time period. So that then the data would always be via MQTT sent into our environment, so to say, and so we could always fetch some time series where we would like to look at. And then the general idea was we're using IBM Bluemix to get the data, to visualize them, and also to analyze them. In the end, we used a little bit different approach for analyzing the data. The data we got here was transferred via Node-RED and then put into some visualization. And the results, visualization stuff is just working. We have not focused too much on it because we also used, for really looking at the long time period of data, Cybus already provided some user interface which were helpful to select the data, so we just, okay, this is working, that is fine. Analyzing the data, yeah, the lessons learned, so to say, it's complicated. There are various tools also in Bluemix. And they do provide a nice infrastructure, but you really have to do the analysis in the end by yourself. You have to implement it by yourself. There's a high learning curve. You have sometimes your own programming languages and stuff like this. So after a while, we figured out, okay, that's maybe a little bit too challenging for this 1.5 days. And we switched the approach and focused on a local implementation. This is working, so it's based on JavaScript, and the idea is first to take 2 time series and compare them. And what we wanted to do then, so that was kind of running end of last day, we wanted today to then do this for all time series automatically, so that we can then say, okay, those values are correlated to each other and others are not. But unfortunately we figured out the library we were using and the correlation we were seeing, they were not really, so we had data which were correlating in the real world, and the algorithm said it's not correlating. So you could see something like those 2 graphs, you can see they're pretty similar. And if you look what the algorithm gave out, it's a 0, 1, 7, it should be somewhere near 1. So that was something, yeah, which was, so we tried to look into that and figure things out. And yeah, my conclusion was needs further investigation. But after I've done this presentation thing, in parallel, so to say, we did further investigations and did with longer time series. And the results were, as I wrote, hope. So we see now with the same kind of data, we get a high correlation. So maybe it was just that, yeah. Now you're confusing me. So I'm done. So it's promising again. So we're up and high. So. Cool.
Next up are the coding agents with Elke, Nikolai, Sergey, and Frank. Please come up. They've got an app to make our daily lives a bit more easier. Das steht. Ich muss gucken, dass es schlecht ist.
Ja, zeigen uns jede Minute an. Ja.
Das ist super. Ja. If you're ready, you can start.
Are we ready?
Ja, ich bin nochmal.
Dann gehe ich auch mal in die Ecke. Wo ist der?
Okay. We've got a lot of data around us and a lot of information coming out of this data. And a lot of companies has been using it for a while. A lot of companies starting to use it. But what's about the person? How can we use all this data, all this information we have? The first step of our presentation will be done by Sergey. No, Nikolai.
So what we did is, we have a lot of devices here which provide data. What we did is we modeled these devices and made something called a digital twin, which is these devices, a model, and they aggregate in this model. The model can consume real data, it can consume prediction data. If no data is available, it falls back to the model. Nice, scientific, but what is the benefit for the user? How you can interact with this? So our idea was, we want to visualize this digital twin via an application. So we started with our Kanban board here on the Windows. This is kind of to do in progress and done. This morning, so most of it is done. And we made a small app which you can interface with your data. We have two use cases. One is thermal modeling and one is electrical modeling. I'm showing the thermal modeling now. Next will be electrical. So the idea is we have these Carlo temperature sensors of the radiators. We want to increase the temperature in the room, and this means the radiator is hot, and then at some point it will get less hot. And in this case, it will stay hot for quite a long time, which means the radiator has not only to heat against the losses from the walls, but also from an open window. So the idea is here, we have 3 radiators, and one radiator, this radiator 3, it will stay with a high power output for a long time. And this we can detect, so we just detect this area, and we should see a message to the user in a minute, which means like, here, are the windows open, check it, please, one radiator is very hot. Which is the thermal model.
That was the song model. Now we'll come to the electrical model. That's Nikolai.
Sergey.
Sergey. Okay. Okay.
All right. So we have developed a model for electric aspect of the energy saving, and it could be really complicated. So we have simplified it over here. So what we have several components of the model. We have battery, could be a huge battery, stored in the house just to store energy. We've got an electric car, a solar panel, and a bike. And there's arrows over here. The blue arrows, they show that 2 objects are influenced positively. So you get a solar panel which delivers energy to the battery, and the battery is charged, so that's positive. And now you've got the electric car and the electric bike, and they consume energy from the battery. That is why you've got a negative impact, like to say negative, because they consume the energy stored in the battery. So that's the basic idea. And you can have a lot of more energy sources over here, but we just thought it would be simpler for you to understand the model, so we reduced the energy sources to a solar panel. All right. Now let's have a look at the app, which is really cool. You can see over here we've got a normal human being who gets off of work at 9 AM and he has to make a choice. Am I going to go by bike or by car? And our app has a priority to power up the bike first and then the car. So we want to make people go a lot by bike and less by car because it's environmentally friendly. Now we've got 9 AM over here when the decision is made. That's when the car or bike starts off for work, and at 5 PM this person comes back So in this period of time, he cannot charge his bike or his car, which you can see over here. And at 5 p.m. he's back home and can start recharging his device. And at this point, I give the pointer back to Anna.
We tested the whole thing, and the test will be presented by Frank, right name.
Yeah, so the question is what it's all about. So it's about control. We don't want to be controlled purely by a computer. We want to have the control by ourselves. On the other side, a computer can help us make good decisions to spend energy. And we made a test. We tried to force you to do something, move around. We did it with our app. And it's the same what we want to do with energy, that we want to force you closing the window or taking the car. And as you can see, such a system is quite effective. So here a user got a notification, and after 2 minutes he stood up and walked around. And we compared it with different users, and I would say between 50 and 80% of the user accepted the notification. And I think we can do the same for cars, taking the e-bike instead of e-car, or closing the window instead leaving it open and put all the heat out. Yep.
Thank you very much.
Okay.
That's a test.
So we worked with the electrical data we got from the RFID data and the radiators. That's it.
Thank you very much. Yeah. Next up, I welcome Nils, Alexander, Tobias, Stefan and Merlin from Team Funberg. Are they here? Yes, perfect. So they worked with some pattern recognition and wanted to do some machine control, if I understood it well.
Yeah, that's consuming the most data. It's enough. So the first thing, we started as Team Skynet, no? So we wanted to build some terminators, no? Going back into time in order to, but it was a little bit complicated to do so, and so yeah, there was another idea, no?
Yes.
To do something, and
yes, exactly. So we are Funberg, we are Skynet, and we also have very big support from Stefan and his son. So thank you for that. We use the data of our unit, of the Funberg cooling unit, and it's not working at the moment. Yes. So that is our cooling unit. Maybe you could see it. And we were thinking, how could we make this smarter? And the thing is, such a cooling unit, which is here, cools down the cabinet. And this is necessary because if you have a production cycle, you have a lot of power, CPU power, there will be a lot of heat load, and you have to bring it out. And the problem is the heat load is not always constant, but it's shifting. And sometimes you have very high impact, and then we have to react to it. The cooling unit itself can react to capacity changes, to higher heat loads very, very fast, but it cannot proact. So it can just react. It sees, okay, now the temperature rises, now I have to cool. And our concept was, okay, if a production cycle is repeating, then we want to proact, then we want to say, maybe you should do something before the high heat load comes, and that's what we did. Because the problem is, sometimes inside there's very expensive stuff inside, and you always want to have a temperature secured, and maybe you say, okay, 36 degrees shall never be reached in this cabinet. And that's why you say, okay, usually you would say, okay, then I want to have a very low temperature the whole time, so that when a heat load peak comes, that it's still buffered. So, and that needs a lot of cooling capacity, and that needs a lot of energy, and that's bad. So we said we want to hold the temperature constant, and we want to act proactively. And to shortly explain, if you have this heat peaks, this load peaks, then you will always have temperature peaks. And in the worst case, they are too high. And what I said, a solution, but not a good solution, would be to have a very low set point for the cooling unit, and then if a
higher load comes, then it just goes up, but it never reaches the critical temperature. But we say maybe it's smarter, you have the same temperature, but you make it very short. You have very short intervals where you have very low temperature, so that you have a buffering for a short time. And that's what we did with Grafana, I think, with a backbone, with Red Node.
Red Node, Influx DB, what we already have seen here.
The algorithm was displayed in C++, I think. Yeah. And usually you would have this heat load, so the temperature goes up. That's bad, that's bad. We want to prevent this. So now, this is, I think this is from a quarter ago. Then you cool down before, and then the temperature rises, of course, because there comes higher heat load again, but it never rises above this, and this is pretty good, because, I mean, this looks pretty drastic. But if you think you would always have this set point temperature, this would be very costly, and if you just do it for a short time, you can save a lot of energy, and yeah, so that's what we did. We analyzed, so we made a visualization with Grafana, exactly. Then we analyzed the data, and then we reacted. Then we acted on the data, and yeah, that's basically our full program. Do you want to add something?
No, from a perspective of a software developer, it was really great because they already have so much knowledge and a little less software technology knowledge. So we cut it down into microservices. Now, so they can go with their C# knowledge, so which I never touched before, to this MQTT services and consume all the data and doing their stuff that they're good for, they know. And we really was on the development side. So this was. Yeah.
And the positive thing is the cooling unit can still act like you have it. Usually, you don't have to go into the control of the unit, but you. From the outside, you set the set point, and this makes the unit smart without touching the unit itself in its inner feelings. Perfect. Thank you.
Thank you very much. So next up is interview with Aditya, Finn, TJ, Daval, and Tulati. I hope I've got that right. And you've been working with energy pricing.
Yeah. I need another plug.
That's a bit late.
Sorry.
Has
anybody
we can use another. Okay.
Plug?
HDMI?
DisplayPort.
Does anybody have HDMI to DisplayPort adapter? Else, can we do it on your PC?
Yeah.
Yeah.
Ah, nice. Got it. Thank you very much. Okay.
Yeah. Hi. We're an interview. We do something with energy data, and yeah. So this is the team. We want to bring transparency into the energy market, especially with grid problems, with the balance between consumption and production. And also to use data from the energy from the EEX, from the Energie-Börse, to optimize some consumption. Challenges in the grid market are currently that there is a price fluctuation from the energy market when the EEG devices are producing a lot of power, like wind energy and stuff like that. Then sometimes the energy price goes negative, and there are some other things. The grid is not always stable, so there's sometimes more power consumption than it is planned to, or lower power consumption than it's planned, and these are costs which come to the grid operator. And yeah, so there's it's difficult to balance between the renewable energy sources and yeah, the actual consumption of the energy. And what we wanted to do is to build some kind of a trigger service to use a lot of data as input to then say yeah, other systems can power on at specific times, and yeah, that's what we did, and we did a lot of other things. So at first we developed based on EEX data and some kind of yeah, web scraping service, notification service to just send an SMS message. Or to call a hook or something like that to yeah, switch on something. So what we did is the service, and our idea was to use also the fluctuation within the grid between the planned and actual usage for sending signals of how much there's over or under planned. And our idea was also to use data centers as to soften the usage while spinning up or down virtual machines which are doing something related to the energy market, like calculating machine learning things or calculating blockchain, which is related to the energy market. Our future scope for it is would be to use it for battery storage or for other things which we can use to yeah, work with the grid balance. And we did a lot of data input from e-mobility and yeah, a lot of other things. So we used tenant data points for the chargers, BMW, and for consumption data. We used the price crawling data and a lot of other data, e.g. unlog lists and stuff like that. I got a point there. And we did some kind of visualization. Oops.
We can also show you more about our demo after this presentation.
Yeah, we did some visualization for data points, and it's not working all like we expected to, but yeah, we did a good start, I think. Yeah, our idea is to also maybe use Cybus for integration into the grid network. Yeah.
That is it.
Thank you. That's it. We got one technical issue with but we will discuss it later. We got some problems with Windows on and the MQTT.
Okay. Thank you. So next up is Team Urja with Anush, Bhaskar, and Vincent. And Urja means energy in Sanskrit.
Yes.
That's got it right.
So, all right, good afternoon, everybody. As you can see, I'm the only person here right now from my team. And I'm going to present about what we were planning to do and how much we reached in terms of predicting heating requirements for a building or a room based on the occupancy and the forecast or weather forecast. So, predicting is not a perfect term. I would say it's more of forecasting the requirements, and it's called PREDIHEAT. It was something we just came up with. So first of all, what challenges we were trying to solve? You need to proactively monitor and forecast what sort of energy requirements or heating requirements are going to be. It has to be real time, more or less, so that you don't either freeze or choke people with higher temperature or lower temperatures. And the idea that we came up with was that we take a look at the historical data, that is historical weather data, historical room temperature data, and historical weather data outside the building itself. So the overall area data, your local data, and what heating requirements were there. For this, we also plan to, or not plan to, we were using RFID tags to monitor number of occupancy or also movement. I mean, we did not reach at that point of time that we can track the movement, but we were tracking, at least we were able to get number for occupancy in the room based on the RFID tags. And then we were planning to run, so here's the fun part. When you go to the implementation part, we started with the idea, like we had a couple of ideas when we started. Let's say we were also wanted to work on desert idea of flexibility with regarding to energy markets, but we then decided as a team that we work on the prediction for heating requirement. We started pretty good actually. There was a huge shout out to coding agents. They actually helped us scrap the weather data from dwd.day. We did not know about it. And then we ran into a problem because none of us are actually data scientists or data engineers. And we wanted to do or run Spark jobs for streaming analytics on the data for more or less modeling and predicting the heating requirements. So yesterday late night, we decided that we fall back to the tools we actually know, which is more or less shell scripts and Postgres. So we ended up using Postgres for doing or making models and making predictions. So there is a cool tool called Orange where you can load up your CSV files and data and create models out of either linear regression or logistic regression. And then there is a nice open source library called Madlib that helps you do, basically the idea behind Madlib is that it helps you do machine learning or analytics on your existing data or existing database. So you take your conventional RDBMS and install this package and you got your analytics right there inbuilt in your package. So you don't have to move data around. So coming to the results part, funny enough, when non-data scientists work on data, you probably have something going very wrong. And as you can see, our data our models were not good. We had pretty much very high error rates or very high inconsistencies. And just to give you a small demo, I hope this is readable. We trained our data on basically room temperature, north-south temperature from the Energie-Campus. So we were using the Energie-Campus data from Cybus, and then we had predictions. If you can see, the predictions are way off than the actual requirement, and that's pretty much it in terms of implementation.
Thank you very much. Next team, Ida Tase Hive-Tech. So Karl-Heinz, Ben, and Paul, please come up here. Small round of applause, please.
So what's the typical approach to analytics, right? There's 3 steps basically always. You go ahead as a company, start it, and you get your group of domain experts that know the field that needs to be improved upon. You get yourself a data scientist, and these guys have to figure it out, right? So there's 3 things. First of all, the domain expert goes ahead, talks to the data scientist, so he understands what the field's about. Next step is the data scientist builds some models and creates some statistics behind it whatsoever. And then in the 3rd step, he has to deliver it back to the domain expert. So in the end, you're able to use the solutions and improve your processes, right? The problem is that from step 1 to 2 and from step 2 to 3, the people have to talk. It doesn't work usually, especially if it's a data scientist and a domain expert, because the domain expert is someone who's usually stuck in physical systems and he knows all the stuff about sensors, etc., etc. While the data scientist is someone who's living somewhere above, like thinking of things in classes and objects and relations, and so it doesn't really fit. And they have to boil down to one level, and they lose information and they lose accuracy. That's why we came up with NetLoom, which is based on OWL standards and RDF standards in order to create one base of language. And with this language, you create basically a huge framework which is really complicated in the detail, but as soon as you apply it through the restrictions, it's hyper simple. You can go ahead, you can create your physical properties as the engineer, like you see your systems, create the physical properties, you create some relations because you know you have some sensors, and they're observed. And the data scientists can come in on this language, based on this language, build algorithms and integrations to data flows, etc., etc. And then the domain expert can come again and consume it by looking at his physical system. And how, for example, one can consume some algorithms, Ben will explain for a second.
Okay. Yeah, if you... Okay. Yeah, we basically just applied our algorithms on the heating data, and yeah, here in the upper region here you see the live trend of the last few data points, and this really nice plot here is an visualization tool which is usually used to analyze data with periodicity. So that's what we have in heating systems, because with night and day the temperatures go up and down and adapt accordingly. And what we did see is that here this blue stuff is the actual historic data from the database of the we had here. And the green one here in the middle, this is the last few data points which we have received. And this model can actually say something about which data points are normal, or if a data point, for example, lies somewhere here, then it's an animal data point, and maybe there's something wrong with the system. And this is really nice because usually we would need a database of labels telling us which data is an anomalous data or not. And with this, we just can apply basically statistics and see based on that which data is normal behavior. So that's basically one of the many algorithms which can be deployed and viewed with our framework. Okay. Thanks.
Thank you very much. Next up is data sickness. We've got Katharina, Sibel, Christian, Samuel, Lars, and Oliver. I'm not sure if everybody's going up. Yes, come on, come on. Give a round of applause. They've been doing some sensor fusion with some sick data. Who would have thought?
All right, I'll introduce what we set up here. We started with 10 sensors just around the building. We installed laser scanners, RFID sensors. We got them all running. We got them all available for everybody. And we'll show you where we started from. There you go. Next. Okay, lower level. 6 sensors. Pay attention on this one. This one's in the hall. We'll come back to that in a little bit. A laser scanner, LiDAR sensor. RFID, 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 LiDAR right there in the back. Next. Upper level, we have 2 RFIDs and 2 LiDARs. And we started with the data. We provided that. It was about 11 million messages that we sent out to the broker this overall weekend. And this is what the data looked like when we started. Nothing done yet. So that's the LiDAR sensor from the hall. Say no live. Okay. Now we'll come what we did with it.
Oh yeah. We thought we would like to extract the dynamics from the scans. We choose laser scanners because they have a wider range than our RFID scanners, and we can monitor the dynamics in the different areas in the building. So as we can see here, we have the scan in red. We have dynamic points, which is a colleague that's running around there. They are marked in yellow, and then we cluster those dynamic points and have a green dot in the center of the cluster for each cluster that is present. So here we can see the path that the person is taking. We did this for our 4 laser scanners in the building, and we also have some laser scanners that have overlapping areas in the upper one. So we thought we could combine them and use the sketch of the building to have an overall coverage. So here we're seeing one person, which is live data. Oh, yeah. And this area is covered by the one sensor, and this area by the other sensor, which is in front of the toilets. So the person is tracked in the entire area.
Live, so to say.
Live.
Somebody is walking around upstairs.
Who's not watching?
Yeah.
Okay, but we thought that's not enough. We really want to do a little bit more, and as it was announced on the Hackathon website, we brought a 3D point cloud with us, and we thought about doing something with this static point cloud and our dynamic live sensor data. And so we took a part of the point cloud and put this sensor data.
Just one step back. What we did is, you've probably seen that online in the viewer. What we did is we took the whole library, put that offline, so we can carry it anywhere. We don't need internet access. We took the model, put it into the visualization, then we said, there was a Saturday at noon, and then we asked ourselves, what do we do next? And then we said, well, let's take the live data and put it into.
Yeah, and this is the result with the live data. And one of our colleagues right now is walking through the hall. Here, as you can see, with the green lines, he's detected. Or she's detected. Pardon? Yes, yes.
That's, by the way, that's the dynamic detection part that Lars just mentioned in the plot before. So we combined that, put that in. It's all MQTT messages. So if next thing is take the whole building, the whole 3D model, put all the sensor data in, and then do even further investigation, which we actually did, because we also did analysis, of course, and this is the path around the fridge. This is the fridge, and we asked ourselves as we looked at the data, who is the RFID transponder with the ending 2F2? Because that was the one that hit the fridge mostly.
Yeah.
Yeah. So sum it all up, 11 million messages. It's more than 70 gigabytes of sensor data, which we provided, put into the network, and yeah, it was a lot of fun. And we'll come back next year.
Next up, last but not least, we've got Team Red. I'd like to welcome Jessica, Klaus, and Markus. And after they've worked on a special user interface last year with Alexa, they've got a brand new user interface today.
So the presentation of SIG is awesome, and now we have less data and more hardware. Some of you remember Team Red in 2016 we've created a user interface with a touch UI with Alexa, and this year we created a whole new interface based on thermochromatic, respectively thermochromic material. So I just need to switch to the monitors. Displaykanäle. No? Switch. Deswegen gespiegelt ist. Remember we had this problem last year. Ah. So. Our requirements. First of all, we have a GitHub project with our sources and our documentation on GitHub, JForge WTD 2017. And our team Red created a project called Request Patch. And we wanted to work on smart environments and natural human interfaces and more haptic devices like this one. This is thermochromic yarn that can change the color based on any signal. And we've created a whole new hardware to control this device, to change this color of this yarn based on the data on this Cybus hackathon. And I tried to signal this. We had some Wi-Fi issues, and we have the methanation device as last year. And the idea is to send an alert on this patch. And this patch should change this color. And I changed it to some alert. And it's an effect you cannot see very good in the back.
Yeah, we had to do some. Such devices are always a pain because you have to switch them on because there's a lot of energy consuming if you're heating up this. Can you send me one, please? And if it works, it should now be more right. Maybe you can see it. We have, yes. Maybe you can see this is a signal we are receiving. So if there's alert or some request to us, you could imagine anybody could stick this to his clothes and get this alert. So additionally, we could say, okay, we got this alert, are going to the place we are alerted to, and we can show it for everybody on the screen.
If you don't see this,
so
we have another sample.
So we are wearing it, going around. We are not. We have no smartphone or something. We just have this patch, which is totally wireless, and you get a signal, and you can say, okay, I'm going to the alert room or alert or whatever we are going to.
Another sample is this one. We had another patch like this, and you can see this thermochromic effect a bit better, like a pulse signal. And this is based on alerts from the methanation device, and we reset this alarm on request. For example, based on a capacitive sensor, we are touching on our bodies to reset this device. So our requirements were to create a whole new hardware sample to avoid some LED Christmas tree at the body, and to ensure that we can create signal transfer on such devices. And we have some more requirements. We wanted to have a good design. In our interdisciplinary team, we have a hardware developer, software developer, and Jessica, our designer. And she created this yarns with her sewing machine. We were the team carrying not only notebooks but also sewing machines to the hackathon. And the solution on GitHub has some Arduino sketch to create some solution for the MQTT connection, and Node-RED flow, like this one, based on some signatures. Another information could be that we want to have some outlook in form of city guides, for example. If you take a patch that guides you to some location anywhere, for example in the airport.
Thank you. Thank you very much. So thank you very much to all the teams for presenting your solutions you've hacked together in just about 2 days. Fantastic. Now we'll take a few minutes, a short break. The jury will go up for about 10-15 minutes, and then we'll find each other back here in around about 15 minutes for the award ceremony. Thank you.
Son, let's go back.
irgendwie? Also kannst du es dann schon anmachen, dann würde ich langsam alle reindrücken.
Ja.
Mach ich mal kurz den Sender an.
Ja. Perfekt.
Halt durch. So.
So, welcome back everybody. Thank you for waiting a few minutes. So, we've had quite some discussions, a lot of writing down and a lot of analytics just to get out the main winners today. And we've got basically 2 steps. First is the main award from Tenet, 2,500 euros Bitcoins for the best team and the best idea. And then we have a few other awards, 9 awards, which each team will get, well, let me turn that around. The winner will be able to choose one of these awards, which are displayed here on the table. And the number 2 will get to choose the next package, number 3 the next package, and so forth and so forth. Right? So kind of first come, first served based on the ratings. So, but first, let's start with the main award, which is, come on, help me. Who is it? Coding agents. Woo!
Thank you very much for 2 days of fun, of innovation, and very good innovation of all the teams that participated in that hackathon. And one winner here, the prize, 2,500 euros Bitcoins. Here a sample, please, that you have something. And happy about the innovation, very good presentation. Next step should be what is really the business value and how it could be realized. Thank you very much.
No, actually, so there's our 2 steps. That was the first step. You won. And now, based on the ranking, on another kind of ranking, based on very, on how's it called? Objective criteria, of course. Innovativeness, the status of the realization, how far have you gone into the implementation, and the third criteria is the value and the relevance of the idea. Thank you very much. So, sometimes things turn out the way they do, which means actually the first team which won this again was the coding agents. Please come back here. So again, congratulations, and you can choose one of the awards. So please stand here and I'll just shortly present. So we've got some embedded vision boards from Basler. Harting Mika, SICK Tim scanner over there. We've got Tinkerbot's Sensoric Mega Set. We've got mini racer car kits from TE. Tinkerbot Sensoric Advanced Builder Set and a football. Some tickets to Pioneers Festival and some Deutsche Bahn tickets, vouchers. A 3D printer pen from Calorimeter. Bluetooth light bulbs and speakers, if I understand it correctly, from Danfoss. So you can choose one of these packages, but we need to tell you that some of these equipment are in use right now, so you can't take it with you right now. We'll have to box them back in and well, give you a bit later. Yeah, we talked about this. So you can choose. And you've got 10 seconds. Right, 30 seconds.
10,
8,
7, 6, 4, 3, 2, 1, bam.
Harting Mika. All right. Congratulations. Thank you. You get the rest later. They are already boxed, okay? There's one missing.
All right. So.
No? Okay.
There is one more, but
I'm from
needs
Hamburg.
to
So
be
you
boxed,
need, you need to wait a second.
congratulations. I think some of them are also empty.
Okay, so just half a point behind them is actually data sickness. Come on up. Yeah, would you like this one? Congratulations.
Thanks.
Congratulations. So, congratulations, and you can now choose your prize. Ten, 9, 8, 7, 6. You've got it? 2, 1.
Bad.
Hey! Very good. Very good choice. All right. Think about sensory mega set. We got this written down. And a football, right? You've got a football team. Thank you. Thank you very much. So the next team with this, the difference between the two next ones was very, very narrow. But up came Vandenberg. Come on up. Congratulations. So, what's your choice? Yeah. Per person, yeah. The Bluetooth light bulb?
Yeah.
All right, good. Very good choice.
Congratulations. One more. Congratulations.
So the runner-up here was Interview. So, what would you like to choose?
I think we take the Mikas.
Mika's already gone. We've got the Mikas already. Sorry about that. And this is already gone. And this is already gone.
Yeah.
So you need to concentrate on this.
We embedded vision.
What?
The upwards?
Sorry, just one update. We have more than one 3D printing pen. So if you want 3, we have 3.
Ah, yeah, so sorry. Okay, so this is a package then in case.
Per person as well.
This is per person as well.
Yeah.
Thank you very much. Okay. 10, 9, you know your job. Thank you.
Yeah, but
4, 3, 2,
6 times.
1.
Good.
Congratulations. Sorry, I didn't go work. Congratulations.
Alex?
It's two-factor
authorization. Thank you. So, next up, Team Red. Are you guys? Thank you. So, what about you guys? What would you take? Would you like to take with you?
The Tinkerbell.
The other one, the Tinkerbot Sensory Advanced Door. All right, good choice, good choice. I think you get a football as well.
Congratulations. Congratulations.
All right, next up, Ida Tase, Hive Tech. So, your choice? They're gone?
They're gone?
No,
No? Sorry, they're gone here. This is gone, this is gone, this is gone.
Yeah. This one? And then this one's gone. A bit of vision, right? A bit of vision.
Well, should we wait for the countdown? Or
9, 8, 5, 4, 3, 2, 1, bam!
You already decided?
So you benefit the upwards, right?
Yeah, yeah.
Okay, congratulations. All right. Next up, Orja. So we've got
tickets and
Pioneers Festival.
Yep.
Nice. Right.
What is together?
The one ticket.
Deutsche Bahn tickets.
I goes together with the pioneers?
Yes, yes, yes.
Okay. How many people are you in the team?
4.
Next up, Orange Mix. All right. Have you worked with that before?
No. Wait. But let him decide. I mean, we are deciding between pens and cars.
Okay.
Are we? Are there other options? No. No. So pens. Are you sure?
Yeah.
I didn't mind cars. Really interesting.
Congratulations.
Awesome.
Congratulations.
Oh, that, you do have a 3. Oh man, you have a 3. Okay, but now you have a portable one as well.
Exactly. Thank you very much. And Tinkerbells.
Yep.
So, please got the Team Mini Racing car. And yeah, there's one more thing I would like to say. So thank you very much. Congratulations. I know you've worked all really hard and really well into this hackathon, and we're very proud about that. Very excited. And we know it's also not the end. You can still work on it, and we are going to do this again, of course, next year, maybe even earlier. We'll see about that. We don't know yet how this is going to happen. But yeah, we had a great time. And I would like to, yeah, sorry. Yes, please, please, give them a, sorry. And before you all run away jumping and screaming because you had such a happy time, we'd very much like you to come and join us outside and make a group photo to yeah, keep everybody together one last time. And one special, okay, there's a small draw we'd like to do really quickly. Okay, so coding agents have a room over there, and they are going to give what exactly? Okay, so sensors for Arduino for the ones who tested their app and help them implement it and yeah, make it better. Thank you very much. So, thank you very much, and we'll have a photo out there before. All right. Group photo at 4 o'clock. We need 10 minutes to change the equipment. Thank you.